In this video, we will dive deeper into SimTalk. The first topic we want to introduce are parameters. You can pass values to a method when the method is called. These values are called arguments. You then have to declare the same number of parameters within the method, and these parameters have to have the same data types as the passed arguments. So first we will insert a source, a station, a conveyor, and a drain. Then we create a new method called calculateCosts. Then we open the method. Since we want to use parameters in the method, we first have to declare these parameters at the beginning of the method. Parameters start with the keyword param, followed by the identifier, a colon, and a data type. Our method will have two parameters. One is of type length, and the other one is of type real. We will call the first parameter length of object, and the second one cost per meter. The identifier serves for accessing the parameter later on. When several parameters in sequence have the same data type, you can list all identifiers of these parameters, separated by commas, followed by a colon and the data type. Additionally, you can also use optional parameters. Optional parameters can be defined by using a colon in combination with an equal sign. If the method is called without this parameter, the value that you have defined will be assigned to the parameter. When we want to call this method, we need to pass these parameters to the method call. In the method, we want to calculate the cost of the object. So we create a variable costs and assign it the product of the length of the object and the cost per meter. The data type of the variable cost will be automatically determined from the value of the assignment. We then want the method to return the calculated costs. You can terminate methods with the return statement. If you want the method to return a value or a parameter, you can add them to the return statement. However, if you want the method to return a value or parameter, you have to specify the data type of the value or parameter at the beginning. So in the line where we declared the parameters, we add a minus sign and a greater sign. Then we specify the data type that should be returned. In our case, it is real. What we want to introduce here additionally is the AnyData type. A variable of data type any can take any value. This can be used if you can't find an appropriate data type for your variable among the existing ones. All provided data types can be found in the Help of Plant Simulation. Therefore, we click on the question mark in the right up corner. Here we can now search for data types. If we click on the first entry, we will then see a list with all data types. We could now click on each and get additional information. Now we switch back to Plant Simulation and can save our changes. To use the method, we create a second method called printCosts and open it. In this method, we create a variable called length of conveyor Then we use the relative path of the conveyor and the attribute length to initialize the first variable. We then declare a variable called costs of conveyor. The difference between declaring a variable and initializing it is that in the declaration, we only define the name and the data type of the variable. When we initialize a variable, we assign a value to it. You can use declarations to avoid incorrect assignments of data types. Since we assign the data type real to the variable, an error would occur if a different data type were assigned to this variable later in the code. After declaring the variable, we assign a value to it. We will assign the returned value of the calculate costs method. So we start typing the name of the method. As you can see, the auto-completion suggests the method. We can see the parameters that the method expects in the brackets. After the minus and greater sign, we see the data type of the value that the method returns. As the first parameter, we pass the length of conveyor variable, and as the second parameter, we pass 5. Then we print the value of the variable. We could also print the method directly. This is possible since the method returns a real value, so the real value will be printed. However, we want to provide more information, so we also print the costs of the conveyor. We show the console, save our changes, and let the method run. As you can see, the costs of the conveyor are printed. When we worked with the debugger previously, we saw the commands step over and continue. Now we want to look at the commands step into and step out. These commands are mainly used when a method is calling another method. With the command step into, we can step into the method that is called. With step out, we can return to the method that called the current method. So let's insert a breakpoint, clear the console, and let the method run. In the current line, we see the call of the calculate costs method. If we perform a step over now, we won't enter the calculate costs method. Therefore, we perform a step into step. And as you can see, we are now in the calculate costs method. Here we could either perform step over steps until we reach the end of the method, or we could perform a step out to directly exit the current method and return to the previous method. So we perform a step out. As you can see, we have now returned to the print costs method. However, keep in mind that in the background, the calculate costs method is first executed entirely, and then the step out is performed. Now we perform one step over step. As you can see, the costs are printed in the console. At the bottom, we see several tabs. The Anonymous Identifiers tab was explained in previous videos. Now we want to look at the Call Stack tab. The Call Stack tab shows the sequence in which the methods are called. The first method to be activated is always located at the bottom of the list, while the top line shows the method being executed at the moment. As we can see, there is currently only one method in the stack, which is the current method. Next to the call stack, we see the Call Chains tab. The Call Chains tab shows methods that are ready to be executed immediately. We now perform a step into step. Then we switch back to the Call Stack tab. Here we can see that the Calculate Costs method is at the top, which means it is currently being executed. And since the print costs function was activated first, it is at the bottom. If we now double-click on it, we would get to the point where the Calculate Costs method was called. To go back, we can click on the active method. We can also see the values of the parameters. If we look at the method objects in the frame, we can see in the top left corner that there is a green point. This point indicates that these methods are currently being executed. We then perform a step out again. And as you can see, the Calculate Costs method object no longer has the green point. As you can also see, there is an Expressions tab. In this tab, we can enter any expression, and the value is evaluated and shown. For instance, we can take the right side of the first initialization, copy it, and paste it into the expression column. Then we will see the value it evaluates to. The Variables tab shows us the variables and their corresponding values that are used in the method. The Suspended tab will be explained later in this video. In the second part of the video, we will introduce the concept of wait. Therefore, we switch to a second already prepared model. In this model, we can see that the production line is split and later merged again. The reason is that the upper line is a line where random inspections of the parts are made. What we want to model now is that every fifth part undergoes such an inspection. To do so, we create a custom exit control for the conveyor and delete the default exit control. First, we insert an if-else statement. In the condition, we want to check if the number of outgoing parts modulo 5 is 0. The modulo operation returns the remainder of a division. The conveyor provides an attribute called statNumberOut. This attribute returns the number of MU instances that exited the conveyor. So we can use this attribute for our purpose. To keep the code understandable for others, we should insert a comment that explains what we are doing. In the first branch, we move the part to the inspection line, which corresponds to the first successor. In the second branch, we move it to the second successor. However, we want to additionally model that the station where the inspection is taking place needs some time before a part can enter it. We could do this in the Setup tab of the station. However, to showcase the concept of wait, we will do it in the method. So before the part is moved to the inspection station, we let the part wait for 10 seconds. After the wait, you can enter any amount of time. Then we insert a breakpoint at the line where the wait is executed, save the method, and let the model run. Since 0 modulo 5 is also 0, the first part will also move to the inspection. If we do a step over, the simulation will wait for 10 seconds and then continue. So the keyword wait can be used to interrupt method executions. Then we can let the simulation continue. Now we want to introduce the concept of wait until. Therefore, we switch to a new model, which is also already prepared. In this model, we will set the processing time of the first station to 3 seconds. What we want to achieve in this model is that there should be only one MU on the conveyor at any time. This could be achieved by setting the capacity of the conveyor to 1. However, in a control, we can make more specific adjustments. We could, for instance, distinguish between different MU, and based on the type of the MU, we could program that only one MU should be placed on the conveyor for a specific type. This can't be achieved by setting the capacity of the conveyor to 1. However, to keep the example simple, we will not use different types of MU. So first, we create a new exit control for the station. We want to tell the station that it should wait until the conveyor is empty and only then move the part. So we insert the wait until statement. The wait until statement suspends the method execution until the condition set in the statement evaluates to true. This means that the simulation continues running and that other methods can be executed during this time. As soon as the condition is met, the suspended method will be woken up immediately and its execution will be continued. In the condition, we want to check if the successor, which is the conveyor, is empty. As always, we use anonymous identifiers to keep our code robust. So then we save our changes and let the simulation run. As you can see, there is only one MU on the conveyor at any time. When you use wait until statements, it might happen that the simulation does not continue because the condition in the wait until is not met. This can happen especially if you have multiple wait until statements in your code. In such cases, it might be very helpful to get an overview of the wait until statements which are currently executed. To understand the state of a model, we can look at the suspended methods and identify if something is stuck. The suspended methods can be seen in the Suspended tab of the debugger. Here we will see all suspended wait until statements, and more importantly, we will see for which condition they are waiting. So we reset the simulation and let it run again. We'll stop the simulation before the first part enters the second station. At this point, the second part in the first station was already processed by the station, however, can't enter the conveyor, since the conveyor is occupied by the first part. So the exit control, in which the wait until is placed, will be suspended. We now switch to the debugger ribbon and click on Suspended Methods. Here we now see the method which is suspended, the caller of the method, and the statement. So in our case, it is obvious that the simulation waits for the conveyor to be empty. However, if you would have more complex models, where the simulation does not continue, it might be helpful to have a look into the suspended methods. Additionally, you should keep in mind that the wait until does not work with any attribute. It only works with attributes that are watchable. To see which attributes are watchable, you can open the F8 dialog of any object. In our case, we open the F8 dialog of the conveyor. Here we now see a column titled Watchable. If an attribute has a star in this column, it means that the attribute is watchable. The next concept we want to introduce is the executeIn method. The executeIn method calls a method or a user-defined attribute of data type method after the designated number of seconds of simulation time has elapsed. What we want to do is to create a variable that tells us how many parts have exited the station. To do so, we create a variable object called partCount and set 0 as the initial value. After that, we create a method called updatePartCount. In this method, we will assign the value of the stat number attribute of the station to the variable partCount. However, we want this method to be called at certain time intervals. Therefore, we can use the executeIn method. So what we want to do is that this method should be called every 10 seconds, so that we can get an overview of how many parts have exited the station. To achieve this, we can use the anonymous identifier self. In a method object that is not a user-defined attribute, the anonymous identifier self refers to the method object itself so we can use self to access the method. Then we can use the executeIn method. In this way, the method will be executed every 10 seconds. However, as you may have noticed, the method is not triggered. What this basically means is that at least one time, the updatePartCount method must be called, so that it calls itself every 10 seconds. Every time you are in such a situation, you can use a method object that you can call init. In certain cases, it might be desirable that procedures are executed before a simulation run starts, for example, to set general parameters of the objects. You can achieve this in plant simulation with an init method. You can either assign an init method as a user-defined attribute to an object or create a method object and call it init. To create a user-defined init method, you could simply open the dialog of the station, switch to the User-Defined Attributes tab, and create a new user-defined method. However, keep in mind that you need to call it init. If you create a method object and call it init as we did, then this init object will be recognized by plant simulation as the init method of the frame. You can also create an init method as a user-defined attribute of the frame. However, this is only supported for historical reasons and should not be preferred. In the init method, we can now simply call our method. We now change the processing time of the second station to 1 second to get more parts processed. If we save our changes and let the simulation run, you will see that the part count will be updated every 10 seconds. However, as you may have noticed, if we leave the init method as it is now, the updatePartCount method will be executed at the immediate start of the simulation, though you might want to execute method after a certain time has elapsed. The initial idea to solve this might be to add an executeIn after the method call in the init method. However, this won't work since executeIn works only on method objects. So if we open the F8 dialog of a method object and then type the letters E and X, we will see that executeIn can be seen here. So we can call executeIn only on method objects. If you would just add the executeIn after the method call, then firstly the method is going to be executed, and then on the returned value, executeIn would be executed. Since our method does not have a return type, void would be the return. Since void is not a method object, we would get a failure. To be able to call the executeIn, we need to prevent the execution of the updatePartCount method. Therefore, we can enter an ampersand sign in front of the method name. This prevents the execution of the method and allows us to call the executeIn method. You might ask yourself now why this was possible in the updatePartCount method with the anonymous identifier self. The reason is that the returned value of self is the method updatePartCount, so it is possible to use executeIn in combination with the anonymous identifier self, which returns a method object. If you want to execute the method in the updatePartCount method, then you need to enter self, execute, in front of the method. In this way, the method object will be passed to the executeIn. So now we can let the updatePartCount method execute 5 seconds after the simulation has started. The init method can also be called with a parameter. This parameter is of type integer. It is used to distinguish between two phases of the init method. In phase 1, the init method is called before the objects have initialized themselves. In phase 2, the init method is called once the objects have initialized themselves. This is useful, for example, if you want to change the failure parameters. You will need to do this in phase 1, when the object has not yet calculated the time for the next failure. So let's look at an example. In the init control, we set the attribute fail interval of the station to 1 hour. Then we add a breakpoint and save our changes. Afterwards, we open the station, switch to the Failures tab, and create a new failure. Now we open the Event Debugger. Here we can see that the init method will be called next. So we perform a single step. As we can see now, a disruption begin event is already queued. However, the breakpoint is at the line where we set the failure interval. This means that the line is not executed yet. However, the disruption begin is already calculated. So our changes won't be applied immediately, since the station has already initialized itself. However, as we stated already, an user might want to change the failure parameters before the objects have initialized themselves. And for those cases, we can use the parameter phase. So if the init method is called without a parameter, then the control will be executed only one time. To be more specific, it will be called once the objects have initialized themselves. And if you use the optional parameter phase, then it will be called twice. The first time before objects have initialized themselves, and the second time after objects have initialized themselves. So we add the parameter phase to our method. Then we insert an if-else statement into the init method and use the phase parameter to distinguish between the two phases. In the first phase, we will set the parameter failure interval of the station to 1 hour. In the second phase, we will enter the update part count method call. Then we insert a breakpoint, save our changes, and open the Event Debugger. Now we see that when the breakpoint is reached, the station has not initialized itself. When we perform 2 step-over steps, we can see that the disruption begin event is set to 1 hour. The method is then called again. If we perform a step-over step, the second branch is entered. So by using the parameter phase, we can call the init method 2 times. One time before the objects have initialized themselves, and a second time after they have initialized themselves. Next to the init method, there are other similar controls. One example is the reset method. Like the init method, you can insert a method object in the frame and name it reset. The reset method will be called every time you reset your simulation. One use case might be if you have table objects in your simulation that are used, and you want to delete the contents of the table when you reset the simulation. Another similar method is the endSim method. This method will be called every time the simulation ends. This concludes our video on Advanced SimTalk.